Hello everyone, I'm Yicheng. Today we got you a demo of a buck converter operating in a continuous conduction mode. Here we have our buck converter demo board connected to a DC power supply and a DC electronic load. And we will be using this oscilloscope to show the measured waveforms. Now let's take a closer look at this buck converter. In this buck converter, we have a high-side switch S1, which is a MOSFET, and a low-side switch S2, which is a diode. We also have an inductor, L, which is this circular component. The input of this buck converter is connected to the DC power supply at this terminal block, and its output is connected to the DC electronic load at this terminal block. We have one passive voltage probe measuring the input voltage over here, one probe measuring the output voltage, and another probe measuring the switch node voltage. In addition, we have a current probe measuring the current flowing through the inductor. Now, let's take a look at some measured waveforms. Here on the screen of the oscilloscope, we have the green waveform showing the input voltage, blue waveform showing the output voltage, the purple waveform showing the switch node voltage, and the yellow waveform showing the inductor current. As we can see from the measurement on the right-hand side, we have roughly 7 volt input, 3.3 volt output. The switching frequency is around 250 kilohertz. The duty ratio, which is the ratio of the on time to the switching period, is around 54%. The average inductor current is around 800 milliamps, which is equal to the current that is currently drawing by the load. And the peak-to-peak inductor current ripple is around 550 milliamps. As we can see, this buck converter is currently operating in the periodic steady state. Also, we can notice that the inductor current is always positive, meaning that the inductor is always conducting current. Therefore, we say that this buck converter is operating in the continuous conduction mode, CCM. Now, in this buck converter, we have a controller that can actively tune its duty ratio in order to maintain a constant output voltage at 3.3 volts, regardless of the input voltage. Now I'm going to increase the input voltage from 7 volts to 14 volts. As we can see here, after the input voltage increases, the duty ratio of this buck converter becomes smaller. This is because for a buck converter operating in a continuous conduction mode, its duty ratio is equal to its output voltage divided by the input voltage. In our case, the output voltage is fixed at 3.3 volts by the controller, and so as the input voltage increases, the duty ratio becomes smaller. Meanwhile, we can also notice that after the increase in the input voltage, the peak-to-peak inductor current ripple has increased from 550 milliamps to 850 milliamps. This is because for our buck converter, its peak-to-peak inductor current ripple can be calculated with this expression. Here, the output voltage, the switching frequency, and the inductance value are constant. Therefore, as the duty ratio becomes smaller, the peak-to-peak inductor current ripple becomes larger. This demonstrates how the change in duty ratio would affect the operation of a buck converter. Okay, so that's all for today's demo. Thank you and see you next time.